Sorry, I'm muted. Hello, everyone. Welcome. David Neff here, and today I am joined with the Dapper Dino. Welcome, Dapper. Thank you so much for joining me, and feel free to introduce yourself.
Well, thank you for having me. I am the Dapper Dino. I have a YouTube channel. That's primarily where I put out most of my content. And it is, I would say, predominantly sort of breaking creationism and anti-evolutionism over the coals. I have had a few somewhat spicy videos about raw mat lately. I do a Tuesday show. So first, third, and any subsequent Tuesdays of the month are Kent with Bent, where my friend Bent Hovind, no relation, and I make fun of Kent Hovind while drinking, and it's still really easy to debunk him, even as I'm getting drunk. And then second Tuesdays of the month, I have Eric with Erica, where we do the same, except it's Gutsick Gibbon and I, and it's Eric Hovind. And I also have uploads every Thursday, and sometimes you can even catch a weekend stream or upload. Depends on what's going on.
Yep. Well, thank you so much. And I guess we'll start with the basics. What exactly is a dinosaur? And what is the criteria for which an animal should be classified as dinosaur?
Well, if you could put up the screen share that I have, that will help. All right. So this is based on a slideshow that I made for a couple debates that I had. So, but it goes through that exact same stuff. So this should work if I am in the right. There we go. Okay, so first we're going to start off actually backing up a little bit. Dinosaurs, which birds are a subset, are archosaurs. And so this is one of the big sort of groups of reptiles. Outside of some sort of weird stem groups, reptiles are largely split into Lepidosauria on one side. That includes things like ichthyosaurs and lizards and sphenodonts and amphisbaenians. And then on the other side, we've got archosaurs, which is crocodiles, alligators, birds, dinosaurs, a whole bunch of things you probably never heard of, like aidosaurs or, I was about to say phytosaurs, but that's not technically true. Phytosaurs are actually just outside Archosauria, but they're close. So we want to take a look, and what does it mean to be an archosaur in the first place? Because this is a group that dinosaurs belong to, pterosaurs belong to it. So one of the big things is the temporal fenestrae, which I don't know if you can actually see my oh, you can. Okay. So if you look back here, there's this hole right here. That's the superior and temporal fenestra, and this is the inferior. Inferior just means below, superior above, Latin. And those were used to attach muscles down onto the jaw. So they actually attach muscles onto the inside, here around on the surangular and the angular, and they allow the jaw to pull up. So that's important for just being a diapsid. But you also have this antorbital fenestra. Now, this primarily is a weight-saving feature of the skull. It keeps the skull relatively strong because there's still sort of a triangle shape with the bone that helps the bones all reinforce each other. But by having this opening, the skull doesn't have to weigh so much. And in fact, in life, it was very likely there was a sinus back here. So this cavity probably was filled primarily with air. Let's see, there's also the palatal process of the maxilla meets in the midline. So that's fairly technical. I don't actually have a good picture for it, but it's something that's happening up here along the maxilla. And not all animals actually do that. Mammals convergently have a similar condition, but there's a palatal process to that. And birds, like all other archosaurs, lack a parietal foramen. So if this bird were actually a lizard, there would be a little hole on top of the skull that allows the pineal gland to have access to light, basically. And Lepidosaurs use it to help them regulate their circadian rhythms. Archosaurs lack this. I think, yeah, we have Thegon teeth on this slide. So one interesting thing is that birds and crocodilians share with each other a particular kind of keratin that is not widely shared in animals. It's beta keratin. So presumably dinosaurs would have had that too. All other dinosaurs. Let's see. Thegon teeth. So Thegon teeth, actually, interestingly, mammals also have this, but of course, if you're a reptile and have Thegon teeth, that's, interesting. And so that means that the teeth are set into a socket. In lepidosaurs, they tend to have what's called pleurodont teeth, which means that there's a groove around the edge of the jaws, and the teeth erupt from that groove. They don't have individual sockets. And also the fourth trochanter. So dinosaurs actually have very specific fourth trochanters, but having one at all is a sign of being an archosaur. See, archosaurs and their close relatives have this unique muscle called the caudofemoralis longus, if I can talk, and it attaches from the back of the femur to the tail, and it's the main retractor muscle for the femur in archosaurs. Whereas, say, humans have retractor muscles on the femur that attach to the top of the pelvis at the anterior end. That's basically what your butt is for. For archosaurs, it goes back to the tail. And so you can see this. This is a Critosaurus, and this over here is a turkey vulture. And you're both looking at the fourth trochanter. And of course, this is Bohyornis, a bird that did in fact have teeth, and they were thecodont. So another really big thing for being a dinosaur, and this is getting out of just being a archosaur and specifically onto being a dinosaur. So the big split between archosaurs is the crocodile ankled and the bird ankled. So the crocodile ankle is what you see on the left here, where you have this is the tibia and the fibula, and then we have the digit bones here. Can I just kind of point? Oh yeah, no, that's better. So we've got the astragalus. Oops, I'm bad at this. The astragalus, the calcaneum, and there you go. Those are the two big ankle bones. So down here is the crocodile version of this, and these bones have a little ball and socket, so it allows the ankle to move around in a lot of different directions and gives a lot of flexibility. But it does not give a whole lot of stability, and it's it's costly in an energy sense to keep the animal upright. So that's one of the reasons why, while you will see alligators and crocodiles walking with their legs directly under the body in what's called a high walk, they don't tend to have that position at rest. They sprawl their legs out. It's because it's fairly energy intensive for them to keep that position. But here is the dinosaur condition. The astragalus and the calcaneum now basically tend to sit flush against each other. And in birds, they are actually fused together and to the tibia and fibula. I mean, the tibia and the fibula.
I'm actually getting a couple of questions from the audience. Show where the tibula is.
Oh, the tibula, yeah. So that's unique to the fossil hominin Australopithecus. Yeah. So there is that. You're going to have to look up that Australopithecus specimen. But so this joint arrangement here only allows the foot to swing in or to rotate in what's called the sagittal plane. That is, if you imagine a plane cut through the center line of an organism, that's the sagittal plane. And so dinosaur ankles characteristically can only do that. Now, this is actually a characteristic that they share with pterosaurs. And that is, they're both in the group Avametatarsalia, which means the bird metatarsal, or Ornithodyra, which is just sort of the bird creatures. So those are two largely synonymous names. Now, another thing, and this is really important. So up until this, pretty much everything here, you could say, okay, well, that's important for being a dinosaur, but other animals have that too that are closely related to dinosaurs. This right here is the really big one. This is an open acetabulum. So here we have an ornithischian pelvis. And so these are the quote-unquote bird-hipped dinosaurs. And so right here, this is where the femur goes into the hip. Now, if you look at, say, a human femur, or really anything that isn't a dinosaur femur, this is a sort of cup of bone. In fact, acetabulum is Latin for a little vinegar cup. So, you know, if you're reclining on your couch in ancient Rome and you decide that you want to spice up whatever it is you're eating, you might want to sprinkle or a little bit of vinegar on it. You had a little cup at the table. And so it's similar in shape to the structure in the hip that humans have. But for dinosaurs, it's just a hole that you can see right through if you have the hip. And this right here is I believe it's a duck pelvis. This is the front end here. This is the hind end here. It's reversed here. So this is the front. And this is the back. And right here, that's the acetabulum. Not this. This is actually just part of the ischium. Birds have weird ischia that kind of flare up, and they kind of cover part of the ilium from this side on view. But yeah, right here. And you can see right through it. And this is actually a commonality that you get in all birds have this open acetabulum, despite the fact that apparently Jonathan Sarfati seems to think that no birds have an open acetabulum. And he wrote a book about bird evolution without actually knowing anything about bird anatomy. But also, I want to talk about this synsacrum. So this is another very key trait for dinosaurs that is not going to be the case for non-dinosaurs. So you can see here that these processes on the spine actually fuse into the ilium, and the spine actually, the sacral vertebrae fuse to each other. So this is a sauropod. I believe this is a Camarasaurus, yeah. And this is an unidentified passerine, so it's some kind of songbird. But it's the same view. We're looking down at the top of the sacral, sacrum, basically. So here you have the iliac blades here. Then here you can see the ischium and the pubis flaring out this way on this bird. And here on this, you can't really see the ischium or the pubis, but these are the iliac blades. And so that synsacrum is really, really key for being a dinosaur. If you have an open acetabulum and a synsacrum, chances are you're a dinosaur. There's really nothing else that has that combination. Now, we're going to get into more specifically what kind of dinosaurs birds are, because we were going to swing this into why is it that we think that birds are dinosaurs? Wow, what makes us say that? Sorry, just had a little sip of water. So one of the big ones is a bone called the furcula. Now, you might know this as the wishbone. So the wishbone is essentially clavicles, right? So you have clavicles. If you feel that little sort of horizontal bone that slopes down toward the middle that's right under your neck on either side, that is the same bone as the furcula. But in many theropods, the furcula is fused into sort of a boomerang shape, like you can see with this T-Rex furcula. Now, for a long time, no one knew if theropods had furcula, but it turns out that a lot of them had already been found. It's just no one knew that that's what they were. But now that we know what to look for, we find a lot of dinosaur furcula. Although also, there have been a few instances where someone thought that what turned out to be a turtle rib was a furcula. So mistakes, they've been made. But another big thing is, and this is actually pretty common to dinosaurs as a whole, is that the radius and ulna are locked so that they can't rotate very much. So if you extend your hand out and you're a human, you can usually turn your palm to face up towards the sky or down to the ground without having to really do anything with your shoulder or move your arm back and forth. You can keep basically your entire upper arm stationary and do that. Dinosaurs generally could not. And it's because the radius and ulna locks together for a similar reason that the Astragalus and Calcaneum were going to lock together. Basically, when you lose flexibility, you gain resistance to injury, and you also tend to be somewhat more efficient because you're not using muscle power to keep your body in the position that you want it to be in. So birds also have this. So birds have actually fairly rigid arms. Basically, past the shoulder, everything articulates together so that as it draws the elbow in, the wing automatically folds down. There's no actual extra muscles. It's all just essentially a bunch of pulleys. And they can't rotate their wrist, just like dinosaurs, because they have a locked radius and ulna. We also know that dinosaurs had an avian-style respiration where they had air sacs throughout the body, and most likely they had sort of a unidirectional flow. So something like a crocodile or a mammal has these lungs that the same volume is right there, and it all leads to the trachea. And when you breathe out and then back in, you're only exchanging part of that volume, right? Because you can't fully, get rid of that volume of air. There's always going to be some air left in your lungs after an exhale, assuming you're not in space, I guess. But birds, and now we know many dinosaurs, perhaps even all of them, they actually had the airflow only joined very late in the whole process of breathing, and their lungs air flowed in at one point, and it flowed out at another, and all of this was mostly powered actually by muscular action all throughout the body, pumping these air sacs. In fact, one of the ways that birds and many other dinosaurs actually got air in and out was basically through limb motion, squeezing on various air sacs. So, and they tended to have very rigid lungs. The lung of a bird is actually mostly incompressible. And that seems to also have been the case based on what we're finding in various other dinosaurs. And so here we have, I incorrectly labeled as an Allosaurus. I believe this is actually a Majungasaurus reconstruction. But we also have, very specific to a small group of theropods that includes birds, is what's called the semi-lunate carpal. So the carpal bones are your wrist bones. And as happens with a lot in dinosaurs, little bits of bone tend to start to fuse together. Like we saw that with the in the foot, where I mentioned that in some dinosaurs, the carpals, or sorry, the tarsals start to fuse onto the tibia and fibula. And here we have carpal bones fusing together, and they turn into sort of a semicircle or half moon, since semi-lunate. Yeah, thanks, scientists. But this is what allows both things like this velociraptor here and birds to fold the arm down so much. So you can see this angle here, but when the bird draws its wing in, this edge of the hand, which is the same edge that has your pinky on it, will actually touch the edge of the arm that has the ulna, which is that same side. Now, if you were to try to do that, you would break your wrist. But this is a common feature between birds and dinosaurs that allow them to both do that. Now, in addition, we mentioned that feathers and scales. So one objection that you get a lot is, yeah, but dinosaurs didn't really have feathers. Well, actually, a lot of them did, and feathers actually are basically just really fancy scales. So they are both crocodile scales, as well as the feathers of dinosaurs, and presumably the scales of dinosaurs were formed from beta keratin, which is a chemical similarity. They also both form from placos, which is an embryonic structure where the skin thickens. So this is a alligator placode. And they both use the same regulatory genes. It's just that the regulatory genes are triggered in different patterns to make scales versus feathers. So basically, a feather really is a scale. It's just a scale that grows in a very particular way. And when we use similar signaling patterns in an alligator embryo, it actually starts to form a simple feather-like filament instead of a scale. So there you go. And speaking of dinosaurs with feathers, we have a lot of examples here. We have Anchiornis, we have Zhenyuanlong. Actually, I don't have this in the right order, do I? It's because this is Caudipteryx. We have Sinosauropteryx down here. We have Eutyrannus. This is a close-up of the feathers from Culindrodromeus, which interestingly is about as non-bird-like as a dinosaur can get. And this is one of the reasons that we think that feathers were probably very widespread in Dinosauria. It's most likely that most dinosaurs had at least some feathers. Now, the feathers on Culindrodromeus are not very bird-like. They were probably stiff bristles that did not have a lot of branching. But it's very likely that the first dinosaurs essentially were fluffy. Let's see. Now, this is not super relevant to the discussion I'm having now, but it comes up a lot with creationists, because creationists have a favorite paleontologist when it comes to dinosaurs, and that is Alan Fiducia. Alan Fiducia is a paleoornithologist, so he studies extinct birds, and basically he is currently the laughingstock of paleontology at this point. He essentially pledged to always say that birds are not dinosaurs no matter what the evidence is. And his last good argument, as far as I can tell, was that the kind of structures that we're seeing here, so like if you look at, they're just bits of fiber for the most part, except here where they're really, really big feathers, was to say that these are collagen fibers. Unfortunately for him, we've actually been able to scan feather impressions like this under scanning electron microscopes, and we find that they have melanosomes. Melanosomes are, it's actually something you have. So the number of melanosomes in your skin cells essentially determines your skin color. So people who have darker skin have more melanosomes. People who have lighter skin have fewer. And in fact, it changes throughout your life. That's what getting a tan is. It's essentially your body is saying, hey, I'm getting a lot of UV here. Let's get a few more melanosomes to try and absorb that UV light before it causes, cancer. So, but collagen fibers don't have melanosomes. And so because we found these preserved feathers with melanosomes, well, they can't be collagen. Let's see. So And this is an example of a life reconstruction of Sinosauropteryx prima, sorry. And the reason I have this here is because this color of the coat is actually based on the melanosomes found in one of the fossils of Sinosauropteryx. So we know it had little raccoon eyes, we know it had a pale underbelly, we know it had a ringed tail. And the reason it's sort of a rusty reddish color is because we can tell which kind of melanosome it is, because there's two basic types of melanosomes, black and rufous. Black is what mammals tend to have, and most animals have, but some animals, including birds, and this is very much not a bird dinosaur, have rufous melanosomes that can make things be sort of a rusty, orangey, reddish color. And those are the kind that we found predominantly in the feathers of Sinosauropteryx prima. So when I was a kid, I was always told that we would never know what color any dinosaur was. Well, we have a pretty good idea about what color Sinosauropteryx was, because we found its actual color cells, basically. So here, I want to do a couple things. One is point out the kind of silliness of people who ask incredulously if Tyrannosaurus evolved into a bird, as well as take a look at what kind of just diversity we actually have in the Are Theropods, which is basically the dinosaurs that are reasonably close to birds, as opposed to things like Tyrannosaurus, like I am, which is actually pretty far away, even within theropods. So on one side we have Carnosauria, and that has animals like Megalosaurus is in Carnosauria. But then we get to Coelurosauria. Now, for a long time, this split was basically just two different waste bin taxa. So way back in the 19th century, Carnosauria was for large theropods and Coelurosauria was for small theropods. And that was not a very good way of differentiating between them. So Coelurosaurs actually you can see enlarged brains, long, narrow hand, kayak-shaped chevrons, and long, narrow foot. So this is the development of these things here. And then the next split that we have here is actually, so this is the first split within Coelurosauria. We have the Tyrannosauroideans way over here, and then all the other things. So basically, Tyrannosaurus is as far away from a bird as you can get while still being technically a Coelurosaur. And so, yeah, we have Tyrannosauroidea over here. We've got, just a bunch of Tyrannosaurus-like guys. We're going to go over on this side. So then we have the Maniraptor forms. And so this is numerous leaf-shaped teeth, another increase in brain size, decreased skull size, pennaceous arm feathers. So what that means is a pennaceous feather is a feather with a vein. So that is, so modern bird feathers, they have the rachis, and then they have a little the feathers, fibers that come from the rachis, and that means that these guys had feathers like that on their arms. So then, going away from birds, we have Ornithomimosauria, which is things like Gallimimus that you might remember from Jurassic Park, as well as some other ornithomimid type things. And then we also have Dinochiridae, which are very closely related to the ornithomimids, and they grew very big and got very big claws. Not as big as Tyrannosaurus over here, but still very, very strange, mostly plant-eating, this group. So then we go over to Maniraptora. So we get enlarged forelimbs, large bony sternum, backward pointing pubis. Now, the enlarged forelimb is actually pretty important. So this is one of the things that people sometimes scoff about, is like, how did you get these, big bird wings from something like a tiny Tyrannosaurus arm? Well, the answer is you didn't. I mean, look where this enlarged forelimb comes in. Tyrannosaurus has been on its own path. Well, the path leading to Tyrannosaurus has been split from the path leading to birds for a long time. So up here we have Alvarezsauridae, and these guys are adorable, and that's all I'm really going to say. But over here we have Therizinosaurida. So this is things like Therizinosaurus and Falcarius. They have these gigantic saber-like claws. They were so gigantic that at first Therizinosaurus was thought to have been perhaps a giant sea turtle. Wasn't even identified as a dinosaur because nothing like that had been found in a dinosaur before. But now we have Panaraptora. And so one of these things is the pennaceous tail feathers. So not just on the arm, but also we have the tail feathers, which modern birds still have in the form of their tail fan. And on one side, we get to Oviraptorosauria. So we get things like Oviraptor. By the way, there's an Oviraptor called Khan, like the villain from Star Trek. Yep. And just a whole bunch of other Oviraptors. Oviraptorosaurias, it's a really cool group. They kind of look like parrots to me. But then we get into Maniraptora, that's where you're getting your dromaeosaurs like Velociraptor, Deinonychus, Utahraptor, as well as your Troodonts, like Troodon. But you're also getting birds here in Maniraptora. So the diversity just within Coelurosauria, which is most of what this is gigantic. And basically every step from this side to this side, we're getting closer and closer to birds. And in fact, in some of these areas, like this animal here and this animal here, have been seriously proposed to simply be birds. And we're getting even closer to birds here with Paraves. So birds are specifically Paravian dinosaurs. This group not only includes animals like Archaeopteryx and Anchiornis, but also forms like Velociraptor and Troodon. And so this is from a list of Paravian dinosaurs, including many birds. So down here we have Gallus gallus, that is the chicken. And you can see that Deinonychusauria goes on one side, and then Aviales, which is the broad sort of bird group, is right on the other side of that. So up here we have Troodontids, then we have Dromaeosaurs or raptors, then over here we have Anchiornis, basically animals like Anchiornis. I cannot say the word, I'm sorry. We got the Archaeopteryx-like birds. So Anchiornis is actually a little bit less like modern birds than Archaeopteryx is. So here we still have these wonderful transitional forms where the wing fingers are still separate, they've still got a long bony tail, but we're getting more and more bird-like. And then we're getting into enantiornithines, which are they're called the reverse birds, and that's because of the arrangement of their shoulder. Their abductor and extender muscles in their shoulder basically work in opposite directions to modern birds. And then we have the euornithines, and down here we have still some things that still have teeth, but they've got, just like the enantiornithines, they have the short tail, and we're starting to fuse the wing fingers down in here. And then here is Aves. All the way down here, this is where we actually get birds. Paleognaths here, neonates here. We've got things like, on the paleognate side, we've got things like ostriches, tinamous, rheas. And then down in neonates is basically everything else. So we've got all of our songbirds, all of our seabirds like penguins, puffins, everything like that down here. So this is a very, very full picture. In fact, the full version of it was just so you could read these names. Like I can tell it's Jingfangopteryx, but it's only really because I know that word and because I know roughly where it should be in Troodontidae. But yeah, the actual original for this was like several thousand pixels tall. It was crazy. And I got it from paper. I wish I remember which one, but I can find it again if I need to. So this is sort of a question for the audience broadly. Is that a bird? So this is Balor Bondoc, which I should have italicized because that's how scientific names work. But, live and learn. So yeah, is this a bird, you think? Like, I want you guys to let me know.
Well, I think it looks pretty bird-like.
Yeah?
The wings and all. It very much looks like a bird.
I would tend to agree. It does look a lot like a bird. Now, to be fair, I did pick a construction of this that is particularly bird-like, but it's actually a pretty reasonable construction, and it's by Gabriel Ugueto, who is one of my favorite paleo artists. His stuff is amazing. But so Danish Debater says that yes, I think it is a bird. So here's the weird thing. It's kind of gone back and forth. Right now, it looks like it's probably a Deinonychosaurian. So this thing is probably more like Velociraptor than it is like a bird. So yeah, the thing is, if you were to travel back in time to like the late Cretaceous, a lot of the animals that you would see, you would probably just describe as birds, but they wouldn't actually be birds by the technical definition that is what scientists would use. And so it really is one of these things where it's just like the transition between the non-avian dinosaurs that we think of, like, Allosaurus or something, and today's sparrow is just so smooth that there is no place where you can draw a line and say, yes, this is definitively a bird, and no, this is definitively not a bird, and therefore just some dinosaur. So yeah. Also, interestingly, Balor. I said it's from Romania, and specifically it's from this place called Hateg Island, which was the largest island in what was then, Europe, which was mostly submerged underwater. And so in Hateg Island, you get all sorts of really weird things. Like there's weird tiny dwarf sauropods, and there are giant members of groups that would otherwise have been fairly small. And we have very strange pterosaurs there. So Jackson Wheat is, I'm getting some feedback.
Sorry.
Okay. My friend Jackson Wheat is actually writing a paper on Hateg Island for his dinosaur class for his master's degree that he's getting right now. So I told him that I better get a copy of that. It's going to be apparently a 20-page paper, and I am going to be diving right into that because Hateg Island is one of the coolest fossil sites.
Very nice.
Yeah.
So I'm probably going to butcher the pronunciation. Nestling 20. What makes birds unique with respect to the extinct birds that went extinct at the end of the Mesozoic? I hear they are toothless and the beak is largely maxilla. Maxilla, however it's pronounced.
So that being toothless and yes, the beak is almost all maxilla. Actually, if we go back to where I had an eagle skull, give me a few. Yeah. So if you look right here, this is the premaxilla. The maxilla only starts back here. So basically, the entire thing of what you would think of as the beak, the actual part that sticks out and doesn't have a fleshy covering, is premaxilla on the top. And of course, this is dentary here up until about here-ish, and then we get the angular and the cerangular, and then you can see a little articular bone here. But basically, by the end of the premaxilla, the sort of cheek is right here. Now, birds don't have a muscly cheek like mammals do. That muscle cheek is actually an adaptation to drinking milk. It allows the animal to create an airtight seal so it can actually draw milk from a nipple, which interestingly is why monotremes don't have muscular cheeks because they don't have nipples.
Interesting.
But I do want to get to what made them survive. So there are a few hypotheses. One of the most recent ones is that the actual aves that we know of from the late Cretaceous were generally small and also associated with bodies of water. And it seems like animals that lived near or around bodies of water or in bodies of water actually did the best in the sort of after the asteroid impact. So it could actually just be that, because in the late Cretaceous, Enantiornithines, which we have over here, were actually the ones who were dominating most of what is now various niches that are occupied by birds. So they were the birds in the trees, they were the hunting birds, they were the birds that would do all the sort of bird things that you normally think of. And basically, the birds that we have now were small, ground-dwelling, and associated with water, and that might just be what saved them, but it's still not really clear. Some of it might just be luck of the draw. And was there another question?
My question is, since birds are dinosaurs, would it be proper to call them reptiles as well?
Yes. Yep. So reptilia is one of those weird words where, like, it has historical use in science, but nowadays scientists only use it sort of informally. Like, you'll see it in papers and whatnot, but it basically now just means the same thing as Sauropsida, which is the group of amniotes that split from synapsids, where mammals are the only surviving synapsids. And then on the other side, you have sauropsids, which include a whole bunch of groups. And diapsids are the only group of the sauropsids that survive today. And diapsids themselves are, today we have, like I said, lizards and turtles and birds and crocodiles and alligators. Those are all diapsids.
Yep. So from what I understand, reptiles are a paraphyletic group and not a monophyletic group.
Well, they're monophyletic if you let birds stay in there.
Interesting.
Because yeah, they're paraphyletic just because we tend not to call birds reptiles. But if you do, well, it's not paraphyletic anymore.
Yeah, interesting. So, let's start. I guess let's debunk the very common myth of soft tissue in dinosaurs with Dr. Mary Schweitzer, because I hear this claim come up in quite frequently amongst creationist circles. So, what exactly is this "quote unquote" soft tissue?
So, basically, in some specific fossils that are preserved in certain fossil beds, and they have specific requirements. One of them being that the area be very high in iron. After essentially dissolving parts of a fossil in acid for a very long time, until essentially all the rock is gone, you can recover stretchy bits of material. And some labs have recovered these as being collagen, which is very similar to a bird collagen. Now, there is the wrinkle in that most of the labs, as far as I know, all of the labs that have managed to recover protein sequences claiming that this is, essentially bird collagen, are also labs that do process bird biomaterial. So it is possible that it's contamination that you're getting in these, but it is the case that Mary Schweitzer definitely recovered small bits of stretchy material when she accidentally at first dissolved fossils. Originally, she had her lab assistant put a fossil in an acid bath to help clear up the matrix, which is the rock surrounding the fossil, because the matrix is usually softer and more soluble than the actual fossil. So you can put it in an acid bath for like a few hours, and it will help loosen up or even dissolve a lot of the matrix. Then you can extract the fossil, clean it off, and have a much cleaner fossil. Well, apparently her lab assistant forgot about it, and they came back several days later, and the fossil was gone, and it all just dissolved into the acid. But there were little stretchy bits in there. So the question then is, how did this material last this long? Because, biomaterial tends to break down. Well, there's a few things. One is that the breakdown of biological material is not automatic. It's usually being helped by organisms that are actually digesting things. So bacteria, fungi, small animals, things like that. So, but if something is encased in stone, obviously that's usually not happening. So that one explanation is just that the method of fossilization actually precluded most scavengers from getting to the inside of the bone. But also the case, interestingly, is that iron has been shown to be able to preserve certain molecules. In some cases, by actually inserting itself into the molecule and helping to stabilize it. And there's no particular known maximum age on molecules preserved in this way. So, and also it's the case that these are fossils that are found in relatively high or iron-rich areas. So then there's always the question, well, doesn't this make us question the age of the fossils? And basically, it's sort of like we found an unexpected result with soft tissue being recovered from some dinosaur bones. It's far from universal, but it does happen occasionally. And now that we know what to look for, we're finding it a little bit more often. So we could do a couple things. We could ignore everything we know from physics, geology, astronomy, cosmology, nuclear physics, biology. We could ignore all of these things and think that maybe this actually means that dinosaurs, only died a few thousand years ago. Or instead of saying that we're wrong about almost everything that science has discovered in the last 1,000 or so years, the other option could be maybe we were wrong about how long collagen can last. Those are the real options. We can just abandon all of science, or we could be like, maybe collagen sticks around sometimes. And so that's the obvious conclusion that the scientific community has come to is, yeah, sometimes collagen just sticks around.
Okay, interesting. So we have a couple of questions from the audience. Danish Debater, how do you go about examining a fossilized protobird? Are there any antidotes that are specific if you suspect it to be a bird lineage?
So first, I'm pulling up here because we have some sort of proto-birds. Now, to what degree something is a proto-bird? Where do you call it a proto-bird and not a proto-bird? if you want to be maximally expansive, I mean, a pterodactyl, which is not a scientific term, but a pterosaur, is a proto-bird in some sense. Its closest living relatives are birds. It's more related to birds than it is to crocodiles. So is it a proto-bird? I mean, it's pretty far away from birds, but kind of. But basically, you go about it the same way that you examine anything else. So you say you have one of these fossils. What you're going to do is you're going to take extensive photographs, measurements. You're going to put all these measurements down. You're going to note what traits it has and things like that. And then once you have all the character states that you can possibly get from it, all the measurements, everything like that, you're actually going to do a cladogram analysis. So basically, you put all of these traits into a chart. And then you use various statistical methods to come up with the most likely, in various ways, trees. So some of the trees are like least change. So what tree do we resolve that has the fewest changes along, basically the fewest novel evolution of something along the tree? There's highest probability, there's Bayesian inference, and all of these can be scored for how likely they are to be just an illusion in the data versus real. And then, generally speaking, you go with the one that seems to have the highest confidence. But these are the kinds of things that you would look for. So, for instance, we have the enlarged brain down here, where we see Spilosauria, kayak-shaped chevrons, and long, narrow foot. So we start looking for that kind of thing. Then it's like, okay, well, do we have the enlarged forelimb, large bony sternum, backwards pointing pubis? Okay, well, now we're getting really close to birds. But, oh, wait, it has the enlarged manual digit 1, and so maybe it's on this Alvarezsaurus side and not going towards birds. But maybe it doesn't. Maybe it has the laterally directed shoulder joint with well-developed semi-lunate carpal, pennaceous tail feathers, etc. Brooding. Then maybe you're here. But then what if it has the boxy skull and no teeth, but it still has a long tail and it has maybe a crest or something? Well, maybe you're over on the Oviraptorosaurus side with, let's see what we can do with Neff, Oidea, and Caudipteridae. I can't talk. Not that these are easy words. And then, maybe you're getting even closer, or maybe you're all the way in this section where we've got things like down over around here, we're getting Picostylia right here. So Confuciusornis and all the other birds that we're getting down here, they have the tail shortened, and the last few caudal vertebrae are all fused together into sort of a clubby thing called the picostyle. Maybe you're all the way down here where you have Enantiornithes, which are basically just birds with funny shoulders. So you basically just have to look at the actual traits that are there.
Okay, and here's another really good question. Another question, Paleognathus is almost exclusively flightless, which has appeared to have happened several times. Is this an artifact, or do they have a tendency to lose flight?
So it's actually not just an artifact. The one paleognath that can fly is the tinamou, and it is similar structurally to some fossil taxa that we think were flight capable paleognaths. And the thing is, paleognaths kind of suck at flying compared to most birds. They don't have a strongly keeled sternum. They're not very agile. They don't have a lot of tight control over their ability to fly. And we see similar, like I said, anatomy in fossil paleognaths. And so loss of flight occurs when flight is no longer really needed to do things like escape predators or get to food. And flight is really metabolically costly. Think about how much energy it takes to jump. Now, to some extent, you can think of flying as basically just continuously jumping, but trying to jump off of air. That's kind of what a flap is. You're trying to keep yourself aloft using only your own energy. And every time you move forward and drop and glide, you are losing some of the energy that you had to yourself add to your flight. And so, while sure, there are some birds that are excellent soarers and will take advantage of like thermal updraft, so they have very low energy flight. Generally speaking, getting into the air and maneuvering in any fancy way is a very costly thing in terms of energy. If you don't have to, you just kind of don't. So you couple that with a group that isn't all that great at flying in the first place, and in many cases, the answer is just, well, stop bothering. Just don't do it. So yeah. Paleonaths do have that tendency. But then again, we also have a lot of flightless neonath birds. I mean, there's a flightless parrot in New Zealand, the kakapo. There are lots of, the dodo was a flightless pigeon. So, yeah, flightlessness is basically what happens when birds don't have to fly anymore. It's sort of a, flight is great and all, but only if you really, really need it. Once you don't, it's gone. It'll go away so fast.
Interesting. So, Jungle Jargon, why aren't you discussing the appearance of the bird Neil?
I think keel.
Keel. Okay, keel. Sorry.
So I mean, so we'll go back a few slides. So the keel is on the sternum. So here you can see it on a T-Rex, and then over here it's on this bird. And so the sternum, you have a sternum too. You got it right in the middle of your chest here. So the sternum is a bone at the center line of the body, and basically some primitive birds actually didn't have keels. So if we go over here, so here we have aviales. So this is the things that people generally are okay calling birds. I'm actually a little picky. Like, I don't actually think that this group is really birds, but you know, whatever. But interestingly, they don't have keels, even though they were known to be flyers, or at least something that could sustain a glide for a very long time by adding energy to it. And so one of the things that's the difference between a glide and a flight is whether or not you can add more energy than you started with. So you're gliding if you're always losing some energy, even if you can add some. If you can't add it at a rate higher than you're losing it, you're gliding. If you're adding energy to the flight at a rate that's higher than you're losing it, or you can do that, then you're flying. And we're quite confident that things like Archaeopteryx was able to fly. And we think Anchiornis probably could have flown too. But the thing is that as you go down this list closer and closer to modern birds, you actually get more and more keeled sternums. So, for instance, Confuciusornis had a weakly keeled sternum. And the Enantiornithines also had somewhat weakly keeled sternums. And the keel is the central line of the sternum develops this process that pokes out from it. And it's where the downstroke muscles on birds attach. So that's if you ever eat a chicken breast, right? The reason there's such a lot of meat at the chicken breast is because this is what the bird is using to keep itself in the air with the downstroke. It has to be a very strong muscle to allow for very, very powerful downstroke. But yeah, so interestingly enough, even with the keel, this is something that has a smooth gradient leading up to strongly keeled modern neonath birds. And like I said, the Tinamou, which is the only flighted paleonath, is actually only weakly keeled, which is one of the reasons it's not a very good flyer. So yeah, I'm not sure if that answers the question. I mean, I guess the answer to the question of why aren't we discussing the appearance of the keel is because I just didn't. I don't know. I don't have a good reason. Because you didn't ask. That's why, Jungle Jargon.
Yeah. Excellent. So we've been talking for almost an hour now. So I guess this will be a good time to start wrapping things up a little bit. My question, kind of wrapping it up. What is your favorite dinosaur?
My favorite dinosaur. I'm going to stop screen share. My favorite dinosaur is, in fact, Meleagris gallopavo.
Interesting. And I guess one last...
That's the turkey, by the way.
Ah, very nice. Turkeys are delicious when Thanksgiving.
Yes, that's why I like them, because they're my favorite bird to eat.
Yes, indeed. I wish they were eaten all year round.
Oh, you can buy turkeys all year round.
Yeah.
Look, any day you can just go to the store and get a frozen turkey. It doesn't have to be anywhere near Thanksgiving.
Interesting. There's doesn't seem to be that many turkey options where I am, unless it's like...
Oh, you need to get a better grocery store, my man.
Yeah, I know. So, how exactly do dinosaurs fossilize? What is the fossilization process?
So it actually varies. The big thing with fossilization is that you need to have the body in a situation where decay is going to be either extensively prolonged or stopped, essentially. So there's a few ways that this can happen. One is if it's relatively rapidly buried. So for instance, one famous fossil is the fighting dinosaurs, which has a velociraptor and a protoceratops fighting preserved in combat. The Protoceratops has its beak around the raptor's arm, and the raptor has its claw up towards the Protoceratops's neck. And they were buried in a landslide. So they were, Mongolia, as now at the time in the late Cretaceous, was mostly a sandy desert. And so something happened that resulted in sand from a dune toppling onto them, suffocating them, and also just trapping them. And so because they were immediately covered by a large amount of sediment, while the flesh surely decayed, bones take a lot longer time to decay. And in fact, they can decay more slowly than sandstone can lithify. And so they are found in what's called aeolian sandstone, which means it's wind deposited sandstone. Most sedimentary rocks are deposited by water, but some are actually deposited by wind, and it's called aeolian. And so they're in aeolian sandstone, locked there. But other things that can happen can be things like a flood can come through, or one thing that actually results in really, really pristine, exquisite fossils is actually animals that fall into lakes that have anoxic bottoms. So if you sink to the bottom of an anoxic lake, very few things can survive where there's low oxygen. That's basically all that's there are anaerobic bacteria. And they will slowly decay the creature, but it's very, very slowly. And if that lake is actively having sediment deposited onto it, that deposition, even if it's relatively slow, might still be slow enough to cover the body before it completely decays. Now, after you have the creature, whatever it is, I keep saying animal, but it works for plants too. After you have whatever creature it is covered in sediment, the sediment has to lithify. So lithification is the process of taking loose sediment and turning it into actual rock. There's a few different ways this happens, but generally speaking, what happens is some chemical that's naturally occurring, and it varies based on which kind of rock you're talking about, seeps between the grains and cements them together as a kind of like a glue. And once this happens, the fossil is essentially trapped in there, and even if it were decaying up to this point, at this point it's probably not going to keep decaying. And another thing that can happen, but doesn't actually have to happen, but it often does, is that some of these minerals can then actually seep through microscopic fissures in the bone and actually start to fill in what was the empty space in the bone. And also, sometimes they'll actually start to seep and replace the actual calcium carbonate of the bone, so that it actually itself starts to turn to rock after a while. But that does not actually always happen. There are plenty of fossils out there where the original, because you got to remember, the calcium carbonate of your bone is basically just a rock, right? That's just what it is. So the actual hard part of the bone, it weathers away, but it doesn't really rot in the same way as other things do, because it's not really digestible. You can't really get energy from it. So, so by the end of this process, you have a bone that's been trapped in rock. It might be infilled by rock, and in many cases, the actual chemistry of the bone itself has been replaced by minerals from the surrounding area that will seep into it.
All right. Excellent. Well, I really enjoyed this discussion. I know you well.
I'm sorry, I missed some of that. There was a lot of weird microphone.
I'm sorry. I said I really enjoyed this discussion, and I hope you did as well.
Oh, I did. I definitely did. And thanks to everyone who came by, because, although, wait a minute. Oh, okay. I was going to say we have 11 people watching, but do we have 11 likes? And we do. So thank you very much for liking the video.
Yeah.
And make sure you like this if you watch it in the future and you haven't liked it yet.
Yeah, and if you want to support my channel, the links to my PayPal and Venmo is in the description down below. And definitely go over to Dapper Dino's channel. His channel is in the description also. And subscribe to both of us. Dapper Dino has a really good channel. And support him as well. You can go to Dapper Dino's channel and become one of his Patreons and join his channel. So with that, thank you guys so much for listening. Dapper Dino, any last words?
Come hang out with me on Tuesday. We start at 5 p.m. Pacific, which is 8 p.m. Eastern. And I'm sorry if you live in Europe. I can only do so much.
All right. Anyway, yep. I think that will give us a wrap. Thank you guys so much for watching, and have a wonderful rest of your weekend. Bye-bye.